We have a theorem that says if S is an orthogonal set of vectors in Rn, then S is linearly independent and hence is a basis for the subspace spanned by S. So we have a set of vectors in S. First, let's remember what it means for vectors to be orthogonal. We know orthogonal is basically an idea of perpendicular, but it says that u1 dot u2 is equal to 0, for example, and u1 dot u7 is equal to 0. Basically, if you just take any two of these vectors and find the inner product, you're going to get 0. Now what we're trying to show is if we've got all of Rn and we've got a few vectors that we're going to call just this set S, and let's say that's 3 of them. All right, so this forms S. But if we take all of the span of S, that's going to be a bigger subspace. And we had a theorem that said a finite set of vectors, their span forms a subspace. So this is the span of S, which we know is a subspace, that is a subset of Rn. And the idea is to show that this set of vectors, we have n vectors, they are linearly independent, which means that the vector, the subspace that they span, they're going to be a basis for that subspace. So basically what we want to show is this set of vectors S is a linearly independent set when they are orthogonal. Now remember, our definition for showing something is linearly independent is to show that if a linear combination of those guys, so we have a linear combination of the vectors in S. If the linear combination is 0, then if C sub I is equal to 0 for all the C, let's say for all C sub I, then S is linearly independent. So that's what we're going to do. All right, so what our first step then is going to be to assume that C sub 1 U sub 1 plus C sub 2 U sub 2 plus C sub n U sub n is equal to 0. Now let me change these to p's because I just realized I had a double use of n. So I'm going to go back through and change all these to p's. This would be u sub p because we're not necessarily talking about an n set of vectors. Okay, so we have that this linear combination is equal to 0. And what I want to do is I'm going to take this 0 vector and I'm going to find the dot product with 0 and u1, which, by the way, we know is equal to 0. All right, so basically I'm going to take this guy right here, which we know is equal to 0, and I'm going to substitute in so that instead of 0, I say C1 U1 plus C2 U2 plus C sub P U sub P, and I find the dot product again with U1. Alright, so I'm just saying 0 is 0 dot U1, but this is our linear combination times U1. Alright, so we know that's equal to 0. Well, I'm going to distribute, and I've got C1 U1 dot U1 plus C2 U2 dot U1 plus CP U sub P dot U1. All right, but the gist is because this is an orthogonal set of vectors, each of these guys, U2 is orthogonal with U1, UP is orthogonal with U1, they're all orthogonal with each other, so each of those are going to equal 0, and what we have is C1 times U1 dot U1, plus 0 is equal to 0. Well, our U sub 1 is non-zero, and so since our U sub 1 is non-zero, that forces our C sub 1 to equal 0. Actually, I probably should have, that's part of the theorem. That's an orthogonal set of non-zero vectors. But anyway, if we assume that those are non-zero vectors, then that forces C sub 1 to equal 0. Now, we got that because we found the inner product with our linear combination of linear independence, trying to assume linear independence, and then we did the dot product with U sub 1, and that forced C sub 1 to equal 0. So I'm going to do that same little manipulation for C sub I as I goes from 1 to P, and what that is going to give us is that our U sub I, all of our S, are linearly independent. Now, we have linearly independent. We already had that set of vectors spans S. So then what that gives us is that S is a basis, since it's linearly independent and it spans its subspace. And what we're going to call it is an orthogonal basis. And we're just going to find that an orthogonal basis for a vector space allows us, it's clever, and it allows us to do some nice calculations. All right, we want to consider an orthogonal basis of a subspace of Rn is a basis for W that is also an orthogonal set. So again, if we have a basis that, I think in the previous slide we called it S, and it's got P vectors in it. All right, so these guys are just, here's our S, a small set, and they span a larger set. We found out that if they are linearly independent, if they're orthogonal and they span W, then they are the orthogonality gives us that they're going to be linearly independent, and so they are a basis for W. And again, this is part of our bigger Rn. So in other words, these are n vectors that we're talking about, but we have P of them that form a basis if they're orthogonal. Okay, so let's think about a Y that lives in W, and if Y lives in W, then it can be written as a linear combination of these basis elements. And again, we're assuming that those guys are going to be orthogonal. So if Y is written as a linear combination of the U's, then as a example, we could say Y dot U1 is equal to this linear combination dot U1, which then we've got C1 times U1 dot U1 plus C2 times U2 dot U1 plus C sub P times U sub P dot U1. All right, but we've established, or we've given, that our U's are an orthogonal basis, and so if they're orthogonal, that's going to go to 0, that's going to go to 0, and we end up with Y dot U1 is equal to C1 times U1 dot U1. All right, so that means we can do a little algebra and get that that first coefficient is equal to Y dot U1 over U1 dot U1. And we could do a similar calculation for all of the basis elements. And so that's what this theorem says, that the coefficients, the weights in the linear combination of y are, so basically each y can be written as a linear combination of the basis elements, but when it's an orthogonal vector, we have a specific definition for those coefficients. So orthogonal basis, we know what those coefficients are going to be, and it's given this way. So it's a nice little orthogonal basis, means that we're able to determine our coordinate vector because we can find those coefficients. Given any two vectors, y and u, sometimes we'd like to write y as a sum of two vectors where y hat, is what we usually call it, is a multiple of u, and z is a vector that is orthogonal to u. And so you can see here what we've basically done is we've taken y and we've projected it into the same plane, and you can see that y hat is since it's in the same line as u, we could say it's a multiple of u, and then this vector z is orthogonal. And so we're decomposing y into two parts where, like I said, y hat is a multiple of u and z is orthogonal to u, which is our other vector. So what we're going to do is we're going to let our z, just directly from this equation, let z equal y minus y hat, and I can think of that as y minus some constant times u, because remember, y hat is a multiple of u, and we want z to be orthogonal to our u. All right, so if z is orthogonal to u, then where z is y minus alpha u, we can say that y minus our alpha times u dot u is equal to 0, just by our definition of orthogonal. And so that means y dot u minus alpha u dot u is equal to 0. And so we get y dot u equals alpha times u dot u. And solving for alpha, we get y dot u divided by u dot u. And what we say this is the projection of y. So y hat is equal to the projection of y onto u. Say. and that's equal to the coefficient of y dot u over u dot u. And remember, that's just going to be a real number divided by a real number, so that's our coefficient times the vector u. So going back to what we have, we started with a vector y and a vector u, and we wanted to decompose our y into two vectors where one of them was in line with u, and that's what we found, and then the other one was orthogonal. And once we find our y hat, then we can just go back and say z is equal to y minus y hat. And we've got our z and we've got our y hat from that. Okay, now we want to compute the orthogonal projection of 1, 7 onto the line through negative 4, 2. So what we were talking about from the previous slide, we're trying to project our y with this guy onto our u over here. All right, so y is 1, 7, and then our u is negative 4, 2, so that's about right there. So if we're doing an orthogonal projection of y onto u, what we want to do is we want to find we want to write y as y hat plus z, where y is a multiple of u. So y is going to be somewhere on u's line. And remember that our z is equal to y minus y hat. Okay, and on the previous slide, we got that y hat is equal to the inner product of y and u over the inner product of u times itself times u. So this part is our coefficient. Okay, well we know that y dot u, that inner product, is equal to, let's see, negative 4 plus 14, we get 10, and u dot u would be 16 plus 4, that's 20. So this coefficient is 10 over 20, or 1/2 times u, and 1/2 times u would be negative 2, 1. All right, so this is our y hat, and notice it is on the same line as u. Just draw here. It's our y hat, and we kind of see our projection of y, that orthogonal projection. Now z specifically is given by y minus y hat, and so the z is 3, 6. So our 3, 6 that's our z.